Tantor Audio, a division of Recorded Books, presents The Science of Fortnite, the real science behind the weapons, gadgets, mechanics, and more, by James Daley, narrated by Kevin T. Collins. Preface. Hi, parent. I say this because most people who play Fortnite are kids, and most kids don't listen to prefaces if they listen to audiobooks at all. If you are a kid and you've actually decided to listen to this preface of your own volition, congratulations. You are an even bigger nerd than me, and I just wrote a book about the science of Fortnite. Anyway, whether you are a parent or a kid, I just want to say hello, welcome you to the book, and introduce you to the overall themes and concepts you'll find in the following chapters. The aim of this book is simple: to explore the various science fiction elements of Fortnite and try to find where they meet, overlap, and depart from actual scientific realities. To this end, we will explore the environment of the island where the game takes place, looking at the storm, the volcano, physics, and some strange otherworldly phenomena that you find all over the island. We will also look at some of the weird and wonderful technologies that exist in the Fortnite universe, such as drift boards and jetpacks, and the iconic battle bus. We will go into great detail about many of the weapons used in Fortnite, making sure to explain not only the scientific concepts behind how some of these weapons work, but also to discuss how understanding the science behind these weapons can help a player do better in the game. While it is my sincere hope that you find this book entertaining, and that you do pick up a few things that help you get a few victory royales every once in a while, the real purpose of this book is to teach you a little about the fascinating science underpinning the world of Fortnite. Many of the concepts explained in this book could easily be the subjects of their own books, and most of them are. Thus, I hope you will forgive any oversimplification, as it is necessary to provide a general understanding of these concepts to the casual listener and Fortnite player, hopefully without straying too far from the wacky, fun world of Fortnite that brought you here in the first place. Enjoy! James Daley. Part 1. The Physics of Fortnite. Gravity. You might not think about it too much while you're wandering around the island trying not to get killed and searching for some sweet loot, but gravity in Fortnite, just like in every other video game, is one of the most important scientific concepts to understand if you really want to master the game. Just like in real life, most people take gravity for granted in video games. If you jump up, you fall back down. If you accidentally slip and fall off a cliff, you drop until you hit the ground beneath you, and if that cliff is high enough, and you don't have that weird special ability where you glow a little and don't take any fall damage, you will die. But why? What's actually happening when gravity is pulling you down toward the ground, both in Fortnite and in the real world? How is gravity different in Fortnite than it is in the real world, and how do the laws of physics apply or not apply in the Fortnite universe? Before we get into all of that, we need to have a little history lesson. Gravity is one of the most interesting concepts in the history of science, and it all started with Sir Isaac Newton and the apple that fell on his head while he was sitting under a tree. Okay, not really. The story goes that Sir Isaac Newton was sitting under a tree when an apple fell on his head, and this made him decide to figure out what gravity is and how it works. In truth, this probably never happened. Much like Benjamin Franklin and the story of how he discovered electricity by flying a kite in a lightning storm, the story of Newton's apple is a nice way to illustrate a complex scientific principle, but it is most likely just a story. What is not just a story is the fact that Newton did, in fact, completely change the way humanity understood the world and the universe when he came up with his universal theory of gravitation. Though the apple falling on the head story is apocryphal, apples did play a role in the development of Newton's thinking about gravity. Newton had been interested in how gravity functioned even before he went to university, and this interest greatly informed his studies. He was especially intrigued by the role gravity played in the movement of stars and planets, and much of his academic work was focused in this area. Even with all of his scientific education, it wasn't until later in his life, when he observed some apples falling from a tree — no, they never actually landed on his head — that he first realized that the same force that kept apples from falling sideways, or even upward, could be responsible for the moon revolving around Earth, Earth revolving around the sun, etc. What was it about that apple falling from the tree that gave Sir Isaac Newton the idea that eventually led to his law of universal gravitation? Unlike the story, it wasn't merely the fact that the apple came down that made him wonder about the forces acting on it. It was the fact that this particular apple made him realize that any apple that fell from any tree at any spot on the surface of the earth would fall in a slightly different direction than all of the others. Now you're probably thinking, wait a minute, that doesn't make any sense. Any apple that falls out of any tree is going to fall down. Well, yes, all apples do travel more or less straight toward the ground when they fall from a tree, but not all trees point in the same direction, do they? No, of course not. In fact, every tree is pointing in a slightly different direction, depending on where it is on the surface of the earth. Think about it this way. Imagine you have two apple trees planted on exact opposite sides of the earth. Let's say one tree is in Wellington, New Zealand, and the other is just outside of Alejos, Spain. Now imagine that an apple were to fall from each of these two trees at the exact same time. What direction would each of these apples be traveling? Would the apples be going in the same direction? After all, they're both falling down toward the earth, right? No, of course they would not be going in the same direction. In fact, these two apples would be falling directly toward each other. If these apples somehow had the magical ability to pass through solid material, they would eventually collide at the exact center of the earth. Just like any object that falls from any other object at any point on the entire planet will always fall toward the exact center of the earth itself. This is what Sir Isaac Newton realized in the 17th century. Some invisible force was pulling everything toward the very center of the earth. All by itself, this realization was not really so revolutionary. After all, humans had known that the earth was round for some time, so it stands to reason that someone, or even many people, would have reached this same conclusion. What made Newton's epiphany so special was that he didn't stop there. He extended this logic to the rest of the known universe, questioning whether these same principles could be applied to the moon, the planets, the sun, and possibly even all of the stars in the sky. What if each of these cosmic bodies exerted the same force from their centers that the earth did? If true, what would that mean for the motion of the planets through the sky, or for the revolution of the moon around the earth? Could one universal, invisible force really be acting upon every single thing in the universe? It didn't take Newton long to realize that yes, such a force acting on everything would provide a much better explanation for the motion of the observable universe than anything that anyone had come up with previously. Newton deduced that the moon must be orbiting around the earth because the earth was generating a gravitational force on the moon, just like the earth must be orbiting the sun because the sun was generating a greater gravitational force than the earth. But we're getting a little ahead of ourselves here. How did Newton get from an apple falling from a tree to a planet orbiting a star? If the Earth was exerting the same force on the apple as the sun was on the Earth, wouldn't the Earth just fall into the sun? To illustrate his ideas, Newton devised this simple thought experiment. Imagine you have a cannon at the top of a tower. Sure, let's make it a pirate tower, why not? And you shoot that cannon precisely parallel to the ground below. What will the cannonball do? You don't need to be a 17th century physicist and polymath to deduce that the cannonball will travel more or less in a straight line until gravity pulls it down to Earth. Obviously, the distance the cannonball travels depends on a lot of different factors: the height of the tower, the weight of the ball, the amount of gunpowder used, etc. But let's say that the tower is 100 meters tall and that the cannonball travels 1,000 meters before coming to a stop on the ground. Now, what do you think would happen if you took that same cannon with the same cannonball and the same amount of gunpowder, but you made the tower 200 meters tall instead of 100 meters, and again shot the cannonball precisely parallel to the ground? Would it travel the same distance as the first one, or farther? It would travel farther, of course. This much is obvious. But why? The reason the cannonball travels farther is that it takes gravity longer to slow it down and to bring it back to Earth. Furthermore, the higher you place the cannon before shooting it, the less the force of gravity is exerting itself as it moves through the air. So now, Newton asked, what happens when we build our tower even higher? What does the cannonball do if it's shot from 5 kilometers in the air, or 100 kilometers? Would the cannonball just keep on falling toward the Earth no matter how high you built your tower? For a while, yes. But what Newton deduced from his understanding of gravity was that, eventually, if you built the tower high enough, higher than any real tower could ever be, the cannonball would make it all the way around the Earth until it came back to the exact spot where the cannon fired. Furthermore, if you built your tower even higher than that, your cannonball would just keep on traveling around and around and around the Earth without ever falling all the way down. This is because, past a certain height, the force of gravity is only strong enough to change the direction of the cannonball, not strong enough to pull it all the way back down to the ground. This is because, at such a distance from the Earth, the amount of force that gravity is exerting on the cannonball is less than the force of the cannonball's forward momentum. You can extend this even further and imagine a point where you could make the cannon so far from the surface of the Earth that gravity cannot make the cannonball do more than slightly bend on its trajectory before hurtling onward into space, never stopping at all. These ideas, and this way of looking at the universe, remained humanity's best way of understanding its place in the cosmos for nearly 500 years, until a young physicist named Albert Einstein came along and changed everything. It's important to note that even though Newton's theories did prove themselves mostly accurate both mathematically and through experimentation, meaning that one could use his universal theory of gravitation to accurately predict the way that gravity would function in the natural world, Newton never really figured out why gravity did all the things that he observed. In a sense, we still don't know everything about how gravity works, but Einstein's theory of relativity did manage to explain a lot that Newton's universal theory of gravitation couldn't. That said, we don't need to throw everything that Newton discovered out the window, or out of a tree, as it were, because quite a lot of his discoveries and innovations still hold true in light of Einstein's discoveries. After all, both Einstein and Newton were essentially looking at the same universe, though obviously Einstein had more data at his disposal, and both came up with mathematically provable theories to explain what they observed in the natural world. For example, it was Newton who figured out that gravity was responsible for the Earth and all of the other planets orbiting the Sun, and Einstein certainly did not contradict that discovery at all. The difference between Einstein and Newton comes when you start to look at why gravity is doing the things it does. There were also certain circumstances in which Newton's mathematical models did not accurately describe everything that scientists had observed in the natural world by the time Einstein came along. When you're talking about Einstein and gravity, it can be very easy to wander into all the other aspects of his general and special theories of relativity, but I'm going to try to stick to gravity as closely as possible. And the best place to start when talking about Einstein's theory of relativity and how it relates to gravity is with the equivalence principle. In simple terms, the equivalence principle states that it is impossible to distinguish between gravity and acceleration. But what the heck does that mean? Imagine you wake up in an elevator, having no idea how you got there. As with most elevators, you can't see outside, you can't hear anything outside of the electronic hum of the elevator itself, and there's no real way of telling what is going on outside of your little box. Now let's say that after you wake up in this strange elevator, you stand up and find that there's a rubber ball in your pocket. Being a bit bored, you decide to bounce the ball up and down on the floor of the elevator to pass the time. As far as you can tell, bouncing the ball in the elevator works the same as it always has any time you have bounced a ball anywhere on Earth. Now let's say that your identical twin is in an identical elevator. At least, it looks identical from the inside, and everything is exactly the same, except that when your twin wakes up, he or she is floating in the air, completely weightless, with no sense of gravity whatsoever. When your twin tries to bounce the ball, it just hovers there, completely weightless. Still with me? Good. Now here's the interesting part. What if I told you that one of the two of you is precisely where you expect to be, in an elevator, in a regular elevator shaft, in some tall building on the Earth somewhere, while the other one is actually in an elevator way out in space, 100 million miles away from Earth? Would you have any way of telling for certain which one of you was on Earth and which one was in space? Obviously, this is a trick question. The apparent right answer would be that the person in the weightless, seemingly gravity-free elevator is in space, while the other person in the elevator that seems to have normal gravity is on Earth. And obviously, if you were to figure out the probability of each scenario, that would probably be correct. However, the question was, can you tell for certain which twin is where? The answer to this question is no. Why? Simple. The gravity on Earth is measured at 9.807 meters per second squared, meters per second per second. Now let's say that the elevator on Earth is in an extremely long elevator shaft, and it is accelerating toward the ground at exactly 9 meters per second squared. Meanwhile, in space, let's say the other elevator has a booster rocket on the bottom of its frame and is accelerating up, or what the twin perceives as up, also at exactly 9 meters per second squared. The twin inside the elevator accelerating toward Earth in the elevator shaft will feel as if there is no gravity whatsoever, because the acceleration is exactly canceling out the gravity of the Earth. Meanwhile, the twin in the space elevator will be able to walk on the ground of the elevator and bounce a ball without being able to tell where they are, because the acceleration exactly matches the gravity of Earth. This illustrates the equivalence principle. There is no functional difference between gravity and acceleration. The realization that gravity was exactly equivalent to acceleration caused Einstein to make one of the greatest discoveries in the history of science. He figured out the reason for this equivalence between acceleration and gravity. Space-time is actually curved, and it's the mass of every object in the universe that curves it. Here is another illustration to help you understand what this means. Imagine a large rubber sheet that looks sort of like a loose trampoline attached at the edges to a circular frame. In this illustration, this rubber sheet is space-time. The fact that it is a two-dimensional sheet causes certain problems in thinking about it as space-time, but don't worry about that for now. Just imagine that space-time, that mysterious stuff that the entire universe is made of, is a big, loosey-goosey rubber trampoline. Now let's say that you have a little yellow marble that is very small and very light. In this thought experiment, our little yellow marble is an asteroid coming from a distant part of the galaxy. This asteroid travels across this particular region of space-time at a very high speed, which we will illustrate by rolling the marble across the space-time trampoline. Now, being that the tiny little marble is the only thing on the sheet, and it is not very heavy, it will roll more or less straight across. For the purpose of this experiment, let's assume that you are not rolling this ray of light marble through the exact center of the trampoline sheet, but a little off to one side. Now we're going to add some mass to our space-time trampoline. Let's say you have a bowling ball that you've painted to look like the sun, and you place this bowling ball right square in the exact middle of your trampoline. What's going to happen to the rubber sheet? Well, obviously, it's going to sink down beneath the weight of the bowling ball, right? Right. So at this point, what will happen if you roll that little marble on the same path that you had rolled it before you put the bowling ball on the space-time trampoline? Will it go straight across, like it did the first time? No, of course not. As the marble approaches the section of the space-time trampoline sheet that is bent under the weight of the bowling ball, its trajectory will curve in the direction of the bowling ball itself. If the marble is going fast enough, it will only curve a little before continuing on its way to the edge of the trampoline, though at a slightly different location on the edge than where it went off the first time. However, if you were to push that marble a little more slowly, or maybe even move it a little closer to the bowling ball itself, the curve in the marble's trajectory would increase, making it turn even further off of its original course. Continuing with this example, if you slow it down even more and move it even closer to the bowling ball, eventually your little asteroid marble will not make it off the edge of the sheet at all. Eventually, the marble will curve all the way around and begin to circle the bowling ball until it eventually falls into it. This is how gravity works with Einstein's theory of relativity. It is the curve in space-time that causes the gravitational force. When that apple Newton noticed first fell from the tree, it was falling because the mass of the Earth was bending space-time. Mass actually bends space-time, causing motion to curve along with it, and the greater the mass, the greater the distortion in space-time. This is why the Sun, which is very, very big, is the center of our solar system, and why the planets, which are smaller, orbit around it, and why the Moon orbits around the Earth. But how does this relate to the equivalency principle? Let's say you take a really, really, really big rubber sheet, like the size of a football field, and you put one bowling ball, one 10-yard line, and another identical bowling ball, the other 10-yard line. Will they begin to move toward each other? Probably not, because they are too far away for their curves to affect each other. They will each be in their own little pocket, not really affecting the other. If you begin to move these toward each other, however, eventually the pockets they are making in the trampoline will connect, and they will start to become attracted toward their counterpart. What is particularly interesting is how much they become attracted to each other as they move closer. If you shorten the distance between the two balls in half, they will be pulled toward each other with a force exactly twice the force they had before you moved them. Similarly, if you were to keep them in their original locations, but double the mass of each ball, the force of their attraction would be exactly the same as it was when you moved them 2 times closer to each other. This is because distance and mass work equivalently when it comes to gravity. This is what Einstein discovered, and what changed so much of how we think about the way that gravity works. Okay, I know what you're thinking. That's all wonderful, but what does all of this have to do with Fortnite? Yes, obviously there is gravity on the island in Fortnite, otherwise everybody would just be floating around all the time. As in any video game, gravity in Fortnite is very important. The game needs to be programmed in such a way to make sure that the players and the vehicles and other objects don't just fly off into the air, but gravity plays a much bigger role in the game than just that. Gravity controls how pretty much every object in the game, players, vehicles, materials, bullets, interacts with the player, the environment, and with other objects. What makes you hurtle down toward the island when you jump off the battle bus? What makes you fall to your death when someone shoots the floor out from under you? What makes your driftboard glide so effortlessly down the side of the volcano? Gravity, gravity, gravity. Sort of. Of course, Fortnite is a video game, so there is no actual gravity on the island. Instead, the physics of the game have been programmed to imitate gravity. But how does gravity in Fortnite work? Epic Games is not spending hundreds of thousands of hours creating a one-to-one simulation of the Earth in order to create enough mass for the island to have its own digital kind of gravity. But efficient use of time is not the only reason Epic does not make gravity in Fortnite an exact simulation of gravity on Earth. If you made gravity in Fortnite the same as gravity on Earth, the game really wouldn't be very much fun to play at all. Usually, people tend to assume that the gravity in a video game would be less than gravity on Earth, because it is seemingly so easy for characters to jump higher than real humans in the real world can jump, run faster than real humans can run, etc. However, this is not the case. In fact, if the force of gravity in Fortnite were less than the force of gravity on Earth, or even the same for that matter, many things in the game would go very, very slowly. The force of gravity on Earth is exactly 9.807 meters per second squared. This means that, in a vacuum, an object dropped at the surface of the Earth will accelerate at 9.807 meters per second per second. If the gravity in Fortnite were the same as gravity on Earth, and you were to build a tower that was exactly 100 meters tall and then step off the side, it would take you approximately 10 seconds to fall to the ground. Now, if you think about that for a second, you'll realize that it definitely does not take that long to fall 100 meters in Fortnite. So how long does it take? Well, based on my own brief experimentation, a fall from 100 meters takes approximately 3.5 seconds, much quicker than it would on Earth. When you calculate gravity with the observations I made during my experiment in Fortnite, you come up with a gravitational force of 28 meters per second. This is nearly 3 times as strong as the force of gravity on Earth. The reason for doing this is to give the game a nice, snappy feel that we have come to know and love. However, if all they did was increase the force of gravity and keep everything else about the game's physics equal to Earth, The last word you would use to describe Fortnite would be snappy. That's because an actual human being that got dropped onto an island with 2.8 times as much gravity as Earth would barely be able to stand up, much less run around.
Sample complete. Ready to continue?